Today's lesson is on functions. Function is a specific type of relation that we learned about yesterday. So a function, as you can see, often looks like an equation. For example, y equals x to the third. And you can input values for x, and then you get output values for y. So here we have a function. The definition of a function is a relationship between inputs and outputs, but specifically in which there is exactly one output for each input. So let me explain what that means. I'm going to draw a little picture, and then I have another definition that sometimes kind of clicks, and students understand that one a little bit better. So here's my little function machine, and it works as you put inputs into the machine. So you're putting values of x into the machine. It works the function, and then outputs come out of the machine, or y values. So think about inputs, values going into your function, outputs, the result after you put your input in. So let's read the definition one more time. There is exactly one output for each input. Or down here, in other words, one input cannot have more than one output. So as you're putting values in for x, you can only have one output. You could never have two different outputs for one input. So that is the definition of a function. So inputs and outputs, there are multiple new words that we're going to learn, and we're going to pair them, which one matches an input and which one matches an output. The domain represents all of the x values in a function, and the range represents all of the y values in a function. And then the input represents the independent variable, while the output represents the dependent variable, because the output depends on the input. And we will talk more about those variables in the next lesson. But make sure you know which words match up with output and which ones match up with input. Here I have a set of ordered pairs, and I'm going to use a mapping diagram to decide if it represents a function or not. And then just remember, to test if it's a function, you have to look, is there exactly one output for every input? So in my mapping diagram, I placed all my x values, smallest to largest, and then I have listed all of my y values, smallest to largest, and now I need to use arrows to match them up. So -2 matches up with 0, 0 matches up with 1, and 1 matches up with 3. So look at your inputs. This input has one output. This input has one output, and this input has one output. Every input has exactly one output, so this meets our definition. Yes, this represents a function. Here's a second set of ordered pairs, and then we're also going to place this into a mapping diagram and see what happens. When you are putting your x and y values in this case, as you can see, the number 2 shows up twice. But in your mapping diagram, you only record it once. So we have 2 matches up with 4, and 2 matches up with 5, and 3 matches up with 6. So think about our definition again. Every input has exactly one output. But if you look here, the input of 2 has 2 different outputs, which means no, this is not a function. Now, instead of using a mapping diagram, we're going to graph a set of points and then determine if it is a set of or if it is a function. We're going to still use that same definition, but we're going to talk about the vertical line test that allows you to tell if something is a function or not, instead of using the mapping diagram. So here I have 3 points. Let's graph these. 1, 3, -2, 3, and then 0, -2. So, go back to the definition. There's exactly one output for every input, and the input are the x values. So, if go to your x values, how many outputs, in other words, how many points match up on the vertical line where that x value lies. So we have vertical lines through your points. And we want to look to see how many outputs are there on each vertical line. Well, in this case, there's only one output on each vertical line, so it matches our definition. So this is a function because it passes the vertical line test. Only one point on each vertical line. Here we have our second set of points, so let's graph these. -3, 1, 0, 2, and then -3, -2. So let's do the vertical line test again. So here's our input. Our inputs, remember, are x values. Let's draw vertical lines. This input crosses 2 points. So that means that this input has 2 different outputs. So because we have a vertical line that crosses 2 points, it goes against our definition of a function. So this set of points is not a function because this input has more than one output. Now we're going to learn about function notation. Here we have an equation, the 3x plus 5. And the function notation, this is just saying that this is a function of the variable x equals 3x plus 5. It's really a fancy way for just writing y equals 3x plus 5. So those represent the exact same thing, but it's just a fancy mathematical notation. But if you have f of, let's say, 2, that is just saying that the x value is 2. So you would plug in 2 for x, 3 times 2 plus 5, and evaluate. So that's all the function notation means. But we're going to do a few different examples using function notation. So example number 1, still using the f of x equals 3x plus 5. But I want to find f of -1/5. That just means solve if x equals -1/5. So you're just going to plug in and evaluate your function. So now 3 times -1/5 plus 5. -3 times 1/5 is -3/5, and then we have to add 5. But how can we write 5 as a fraction with a denominator of 5? So I've changed my 5 to 25/5. So now I can add -3 plus 25. So 22/5. And then I can change that to a mixed number. 5 goes into 22 4 times. 2 left over, 4 and 2/5. I will also accept the decimal, which would be 4.4. So f of -1/5 equals 4.4. For this example, I have 2 separate functions. I have f of x equals 4x minus 1, and then g of x equals 3x squared. So whenever you're dealing with more than one function at a time, we represent them with different variables, but they're the same thing. It's just function notation, two different equations. And I want to find f of 2 plus g of 2. All that means is we're plugging in 2 for x in the f function, and then you're plugging in 2 for x into the g function, and then you're adding those two solutions together. So, plugging in 2 into the first function, I will have 4 times 2 minus 1, which 4 times 2 is 8, minus 1 is 7. So f of 2 equals 7. And then g of 2, plug in 2 for x, 2 squared is 4, and 4 times 3 is 12. So g of 2 equals 12. Going back to the original question though, we want to find f of 2 plus g of 2. So all we're really doing is 7 plus 12, which equals 19. For our third example, we have the function of x equals x squared plus x. And we're evaluating this function of 5y. So we're plugging 5y in for x. So f of 5y equals, plugging in, we have 5y squared plus 5y. So now let's evaluate that. 5y squared means 5y times 5y. Now if I rewrite this, I can do 5 times 5 times y times y. So 5 times 5 is 25, and y times y is y squared. 25y squared plus 5y. And I can't do anything more with that because I don't have the value for y, and I can't combine like terms. So right there is my final answer. Okay, here's our last example using function notation. Find g of negative 4, so plug in negative 4 for x, and then plus 7 you'll just add at the end. So 2 minus negative 4 squared, that's going to give us g of negative 4. So negative 4 squared is a positive 16. So 2 minus 16 is negative 14. But then we have to add 7 at the end. Add 7. So negative 14 plus 7 is negative 7. So there's our answer. So today's lesson was on functions. You need to know the definition of a function and determine if a set of values is a function, and then evaluate functions using function notation. Good luck with the lesson.